Cool. Stream, I think is set up. Let me just get a few things. Can you all hear me all right? Just want to check. There's a filter on the audio because my computer is making a ton of noise with the fan. So I just want to check. I think it's a little low. Well, I mean, the audio sounds fine on my end, so hopefully that's good. Uh, so yeah, I mean, mainly what I want to uh, just, I don't know, just kind of have a casual stream where I kind of code a DIT-like architecture, and so like Stable Diffusion 3 is this parallel stream. Let me just pop up the diagram here. So yeah, I mean, we all know that Stable Diffusion 3 is like this parallel stream uh, architecture, and I kind of have some code written for that right now. It's not really. One second. Sorry, I'm a little sick right now, so you may hear it in my voice, but uh, I mean it's not bad. But anyways, so yeah, you have this parallel stream architecture, and I want to code just one stream for um, the image part, and the second stream for the text part maybe later. Like I have the two stream architecture working right now. The code isn't fully fleshed out right now. I mainly want to get the code working like a lot better than it is now, more optimized. I mean, adding the second stream is really annoying because you have all of these things you have to deal with, and that becomes a problem because this model already takes up a ton of memory on your computer, and these models here, they take up a ton of memory even whenever you're not even training them, you're just doing inference, and yeah, that's just annoying to deal with. So I have some code to deal with that. I know in the original Stable Diffusion paper they just went through the entire, I think it was 20 million images that they have. It's CC12M plus Imagenet. I don't know which Imagenet they do, but they combine those and they just iterate through the entire dataset and pre-compute these embeddings. I personally didn't really like that in case I wanted to edit it, so I have something else, but I want to do that later, maybe in a second stream or something. So this first one, I mainly just want to take ImageNet. I want to. I have I have all the code written out, so I know that it somewhat works at least. And then in the end, it would be doing inference with that pre-trained model that I have, and just kind of code it, talk through it. Um, if there's any questions, I'd love to talk about it, and if there's anything that I remember, oh, this is interesting. Whenever I was coding Stable Diffusion 3, I'd love to talk about that. But yeah, it's just a single stream right now. So yeah, let me just get started with coding it. So, the way I code things is usually like a depth first manner. So starting from like attention and then coding from there. Oh, thank you. I have the comments up on or I have the live stream up on a tablet beside me. So thank you. I appreciate that. Yeah. So let's get started. Yeah. So this will be super casual. So if y'all, I mean, if y'all want to just throw comments and just chat with me, that would also be really cool. Just be super casual and laid back. Um, so yeah, let me just do. Let me just start with attention, and we'll just start coding from there. So, I mean, good old attention. The nice part about having a your stable diffusion 3, with the stable diffusion architecture, is you just have 256 by 256 images that you pre-train with. So you don't have to worry about masking in a causal manner, and it's just super efficient. So I'll just start with that. Uh, I have two things that I didn't code, these rotary embeddings, because Lucid Rains has an insane implementation that like I implemented rotary embeddings, and I'm just like I'm just gonna take this one because it's so good. And then the original Stable Diffusion 3, whenever I was trying to do absolute embeddings, you'll notice in the paper they use absolute positional embeddings. Uh, these embeddings are just absolute. Like you don't see the rotary embeddings over here. The Flux model does have these rotary embeddings. So I added rotary embeddings, which made the model better. So I'm using that instead, which comes from here. But this part is in case you want to use absolute instead. So, and then I'm going to also add flash attention. Import flash attention, and I think it's this one, and flash attention function. Blocks, Patchify. So I have, yeah, so I'm going to add some functionality for flash attention. Whenever I originally trained this, I didn't use flash attention. So, and there's a kind of a discrepancy between the code I had and the flash attention code. I don't know exactly what the discrepancy is, but if you try to do inference with my model using flash attention, the pre-trained one, it doesn't work. I'm guessing there's some scale factor in flash attention that is kind of hidden, but I mean I'll talk about that whenever I get to it. But yeah, I think it's I don't know exactly what the discrepancy is. Yeah. So I can go through rope real quick. So let me go and download the rope paper. Oh, got it. Yeah. Let me download the rope paper. Hey, how's it going, y'all? Oh, so I'm basically going through. So I have Stable Diffusion 3, and I'm basically coding through. I'm just coding a single stream Stable Diffusion 3 DIT to just do inference to generate images from not text, but from a class label. So say I have 1,000 classes. I want to take one of those classes and generate an image of that. And I'm just doing one of the streams here instead of two streams. Oh, is the audio bad? Let me try to fix that. Oh, yeah, that may be my bad. Increase the noise. Uh, Hopefully the audio sounds better now. I have a filter, so hopefully that can block it out. I increased it, so it'll hopefully be better. Yeah, so I don't. Okay. More. Yeah, I'm in my computer, since I'm using the GPU for OBS and the camera, it's dying. Uh, the fans are just on. That's probably what you hear. All right, cool. All right, cool. Let me know if the audio is bad again. Maybe the fans kick in. Yeah, let me go get the rope paper real quick. Just real quick. Oh, it's the mic. I'm hoping it's not terrible because I don't know a second mic. Hopefully. um. So okay, cool. With next time I'll try to get a better um the old headset. This is the headset I used to use. The other one I don't have on me. One I mainly but also in videos I typically go over the audio again and yeah. So I mean normal positional embeddings, they usually you usually have this sinusoidal embedding that you add. So if I have imagine I have 512 dimensions. For each dimension, I can add a sinusoid going over time. So I have so if I have a sequence like 1, 2, 3, 5, I basically want to add a unique embedding for each of these positions. And to do that, you can basically, let's say I don't know, I can basically have a sinusoid that is in dimension 1, and I can sample that sinusoid 5 times. Imagine I have a sinusoid I that I create, and I just sample it 5 times, and then I have an even faster sinusoid. I sample that 5 times. I have an even faster sinusoid, and I sample that 5 times. You'll get a unique position, or you'll get a unique three-dimensional vector because you have these three sinusoids of varying frequency represent each of them. Now for rope, the idea is I have, say, 5 of the X tokens, and diagram. Basically, I'm going to rotate them based off the relative position from each other. So if I have a vector here, 6 vectors, I want to I want to rotate more if it's further away. Basically, have this decay in so you basically encode this via rotation, and you say the rotation is based off how far it is in the sequence. So the word width compared to so if we use width as the base word and we the other words as words we're rotating, then transformer would be rotated 1 rotation, whatever that may be, theta, and then enhanced would be rotated twice. That's kind of the idea behind these rotary positions. You're just rotating the vectors relative to each vector, to the other vector. So you have so instead of having absolute embeddings where it tells you how far you are from the beginning of the sequence, it tells you how far you are from the current word. And that's what this, so I give it the entire sequence and it outputs these vectors for me, and I just add them to the vectors I'm doing attention with. So yeah, continue coding attention. So I'm going to add positional and I'm going to make this absolute or relative. So that'll give you either the absolute positional encoding stable diffusion 3, relative positional encodings, the flux use. And so basically we just need the dimension normal attention. And yeah, I'm using torch because it's a lot harder to code any quickly in TensorFlow. Yes. So the head dimension is just the dimension divided by the number of heads, and the scale parameter we're going to have is 1 over the square root of dk. So that's, go to the paper that I have here. You divide by the dimension scale that we're going to have here. So now we need the projections. I'm just using the query, like you usually group these to make them faster. I'm just going to have one, like one for each. So you usually group query key value projection and one a lot faster on hardware, but I'm just going to have one projection for each, just because it was easier to debug. I was playing around with the embeddings themselves. And then we also need, so if we look at the paper, and you see this now, I forget how long ago, but you get these instability issues with attention if you don't add norm. So if we look at this left side here, this attention block with the this is the value, and we just look at the left side, you have this norm and this modulation, and then this is fed into just our pre-norm, and linear layer does the query key value projection, and you have your RMS norm of your stabilized. So these will be our RMS. So then I'll add, so if we have rotary position, then we want the rope embeddings to be part of. I need to. So I already have that. Mainly, I didn't want to code that from scratch. So now it's just good old attention. I bet whoever Copilot can project, reshape, not do the norm. So we need to do the norm. Self dot k norm. Oh, okay. Let me fix. That should be better. Yeah, it has a little noise to it in the background. This, hopefully, yeah. Hopefully it's still bearable. I need to get so I usually move around a lot. So I record in various places, so it's hard for me to kind of bring a mic around with me to a bunch of places. But I need a stationary mic I can kind of. That's actually really good. I usually have to use these mics in a headset, which are not as good as a good mic that's just stationary. Um, yeah, so that's why I ran into the feedback problems. Anyways, let me know if I still have the drop off problem. But yeah, so query key value projections here with the norms. Yeah, reshape. I do not like this. So queries are equal to queries dot reshape. So we're going to add the heads here. So this is just the projection with the norms, and then we add the heads. So nc self.num heads and self.headDim, and then we transpose it. And nc d is equal to x.shape. So our input is going to be a set of tokens that represent our image. So that'll be of shape batch by the sequence length by the dimension, and I'll add the patchification later. Like I said, I do depth first, essentially whenever I'm coding. So I start with the basic attention part, and this is just adding those heads here. So this here, we just need to rotate it. So queries are equal to self.rotate embeddings, and this is just .rotate queries or keys. Let me do the same for the keys. And then we just do normal attention. So I have, like, flash attention is here, and it does work for me whenever I use it because, like, it is GPU based, like y'all were saying. It does work on my GPU, but it's not the, it's a little different than the normal dot product attention. I'll just go ahead and write out normal attention. I typically do .mt here, and this is where our scale comes in. Then you just do, I'm not going to worry about the mask because I'm not doing various sequence lengths, since I'm just keeping it at 256 by 256 resolution. I don't really feel like changing it from that. It makes it more annoying. I'm using 3090. I think it was 3090. Yeah, and it works on there. Yeah, I trained this on 8 A100s within like for a day, and it also worked on there. Most things are built for like A100s and H100s. But I think it has to work with some of the newer versions as well. And one thing to note is you have to make the flash attention. You have to make it float bfloat or float 16, bfloat 16 or float 16. So like I can write it out real quick. It's the flash attention function of queries, keys, and values. You can make it causal if you want, and you can add the softmax scale, which is equal to the scale. But you have to convert these to floating point to float 16. And you may also have to download the right CUDA version. I'm using my school's computer for the A100s right now, but I would probably be using like Google Cloud or AWS or something in the future. They're expensive. I would much rather not spend that much money, so I'm just using my school's computer for the A100s right now. I was able to get access to run on there a little bit. Yeah, so I mean, if flash attention isn't working and you have a compatible GPU, I think they have a list of compatible GPUs, then like make sure your CUDA version is aligned with your Torch version. That's an issue that I had a lot. So just check that. Yeah, so this is just reshaping it back. So yeah, project. This needs to be queries here. Key values, yeah, query key value. We're normalizing the queries and the keys, and we're reshaping it, adding the heads. We're adding the rope embeddings right after. Then we do attention here. I'm going to remove this line here. Yeah, so normal attention. And then we're just reshaping back and doing an output projection. So pretty standard. This should actually be transposed. I don't know why it did that. It should be transposed and then it should be reshaped. Copilot is not having a good day today. Yeah, so that's that. Cool. Let's move on to the MLP. So that is just this part here. Oh yeah, The S3 storage, it like looks, it doesn't look like a lot, and I decided to store a data set on there, and that cost me. That was not a good idea. Uh, I ended up just storing it like on Hugging Face because that's free. As long if it's public, you can store like any size data set on Hugging Face. Like I'm recaptioning some Imagenets for Stable Diffusion 3, and I'm recaptioning Imagenet images, and you can just store that on Hugging Face. I also want to open source it, so that's another thing. Yeah, so we did this part here. I'll add this normalization stuff later, so this is just attention. They do an MLP, and I think they mentioned they use Swidelu. I don't know why you wouldn't use Swidelu. So Swidelu. You can just import a Swidelu library, but I'm gonna manually code it. Yeah. Yeah, yeah. I think you can store a good amount on Hugging Face if it's private, but you end up having to pay for things if it's private. I don't know if it's cheaper. It probably is cheaper than AWS. AWS is pretty brutal with their prices. Yeah. So MLP, self dim. I like to do a hidden scale um, rather than the exact size. And I'm going to add two activations, a Swidelu and a normal GLU, just because. Yeah, I'm not doing that. So the projection size is equal to just the dimension times the hidden scale, and then we got our activation function here, which is just act. And if this is equal to Swidelu, then we have we have this up projection, we have the gate projection, and then we have the down projection. So I combine the up and gate. I don't know why I combined it here, but not in the attention version now. Yeah, so this is going to be the projection size times 2. It's the gate and the up projection combined, and then we have lin down, which is just going the other way. And then we have the activation function, which itself is Silu. And I guess I don't need to add the GLU version. The GLU version I didn't use. It was again for testing different variations of architectures, which was just, can I add a GLU and like how much better is Swidelu for a basic task like this? Yeah, so if I don't have that, then I just won't worry about it. This is just wrong. So we have the up projection, and we have the gate is equal to this, and we're going to chunk by 2. Or we can do split self dot projection size on the last dimension. And then we just do a down projection. Yeah. So then you scale, and then I think GLU and Silu and like are basically like they don't really. There isn't much of a difference in terms of performance from what I've seen. Generally, you just use Silu. So I don't know. That's not something I can really speak on. Why do you not use GLU instead of Silu? I'm not particularly sure. They both work really, really well. There's probably some like they both look pretty much the same. Yeah. So you could probably throw GLU here and it would work just the same. So yeah, we need to throw this through the activation function, and we need to, that should not be up projection. The activation is the gate. So yeah, we have this up projection, we have the gate, which are just the same projection, and we have the up projection, and we have gate here, where the gate goes through the activation. Yeah. Yeah, and if you look online, this is what you see. Actually, I think it should be the other way around, where this is the activation function should be around here. But one of them goes through an activation function, one of them doesn't, and one is basically the activations, so that's why I think these should be renamed. And the other is the gate, kind of saying, like, emphasizing some neurons and decreasing other neurons. So that's what you have here. And then this is just going to return the down projection. Down projection of the up projection output. Yeah, so that is really simple. That is just the MLP. Yeah, simple MLP. Now let's add the norms. So you see these norms all over the place. You see this modulation. I'm gonna add. So basically, the modulations are this layer norm plus mod, and it is a normalization like you do with normal layer norm. So the mean, shift, and variance scale for every vector. So you shift by the mean and you scale by the variance for your layer norm. And yeah, subtract mean and divide by the variance. But then you usually shift and scale by a learned parameter. But instead of doing that, you shift and scale by the, like, you have this class do the shifting and scaling. So you have this class here, which is usually your text, and it's usually your text output. So you have this text output, which I'll talk more about later. But you have this text vector representing what you want to generate, and this vector will be passed through every single block, and this text vector is going to control the statistics of the input to every block. So it kind of allows it to, I guess, choose what blocks it wants to utilize more or less in a way. I guess that's probably how you can kind of think about it whenever you have this vector here. So this vector basically allows the class to control the entire architecture, or allows the class to dynamically control the inputs to the architecture for every layer. So that's what the norm is. And the norm's really simple. It's just a layer norm. Norm.py. A layer norm and then 2 linear layers. So import torch, good old ports. Define init. And we're going to take in the dimension and the C dimension. So the C dimension is, like, that'll be different. It can be different than the actual dimension of the model itself. So that's why I have both of these here. Yeah, so we need a layer norm here, and I'm going to remove the element-wise affine, just so that we only have the class actually changing the statistics instead of having learned parameters do that. And then, like, you don't need these parameters since the class is already the class is what you want to change the parameters. So self.c shift is going to be this linear layer, which takes the C dimension and projects it down or up, depending on what that is, to the model dimension, and you have the scale, which does the same. So our forward method, I called this y. This will, that's mostly good. Yeah, so it normalizes this, and remember we don't do the element-wise affine, so it just normalizes it by shifting by the mean and scaling by the variance. And then we get the shift and scale from the class vector. And then we are going to, and that's almost there. So first we're going to scale the vector. So this is like so we scale down to unit variance, and then we're going to scale up to whatever variance the class wants. But I'm going to add 1 to that so that the initial model the initial model is initialized around 1, and this is what you usually see. So it's 1 plus the scale parameter, and this means that it'll stay around, like, since the weights are usually initialized, so such that the magnitude is less than 1, like you usually have smaller weights, then this will probably like decrease the magnitude if you don't add 1. So, or decrease the variance even more. But if you add 1, then it keeps it around 1, and that's generally better for initialization. And then here this is just adding the shift. And one thing to note is this is a vector and this is a matrix, and this is a matrix. So x is of size sequence length by the dimension. Y is of size just the dimension. So this is just a vector. So that's why I'm adding this extra dimension here. And this is the batch dimension. So this is just adding this extra dimension where it's doing this shift and scale for every part of the sequence in the same way. So x times the scale plus the shift parameter. So simple norm. All right, now let's do the transformer block. So the transformer block is probably the most important thing. So this code's going to be quite a bit longer than the others, but it's just using. Actually, no, it's not that long. The diffusion model one is very long. This is just taking all the blocks that were created and putting them together. And there is this path issue I was running into whenever I was coding it. I didn't really feel like fixing it, so I just did this. It works good enough. Attention. We'll import the MLP. We'll import the norm. .blocks.norm. Import norm. And I'm also going to show you this xformers implementation. Swidelu op, which is, I think, exactly the same as the one I had. I think it's, but xformers is crazy optimized, so if you are actually training it, you should probably use xformers. I was like I said, I was doing tests, so I didn't actually do that. Self-dim, cdim, wad, wrong place. Define init. Wad the hidden scale, which I set equal to 4. Wad the number of heads equal to 8. I'm not going to make this causal. I'm going to add some positional encodings. Make that absolute, and the activation function. I'm just going to keep that as swidelu, so I'm not going to worry about that. And then I'm also adding a layer index. This is just for debugging purposes. So normally what you would have in the Stable Diffusion 3 paper, for every block you would have 2 streams. So you would have basically 2 of these blocks for 1. So you would have 2 layer norms, 2 pre-layer norms for attention. You would have 1 attention layer, but you would have double the projections. You would have double the double the input projections, double the output projections, double the norms. So the parameters are basically double in general. Flux kind of mitigates this by only having some parallel stream blocks and having like I think it's 1/3 parallel stream blocks and 2/3 single stream blocks, where they only have one of these streams and they concatenate the text and the image and work with that. So that's a lot less parameters that you have to deal with. If I were to run that on my computer, it would probably die. I don't think it would work. Yeah, so let me go ahead and code this. So it's just 1 block. Make the MLP here. Scale. The activation is going to stay swidelu, and we'll add attention here. It's equal to attention, dim, number of heads, positional encoding, and the layer index. Self.norm1. So we're going to have a prenorm for the attention and a prenorm for the MLP. And finally, we're going to have some scale projections. Scale 1 is equal to a linear layer of cdim by the dimension, and I'll show you where these come from in a second. And yeah, let me just code up the forward method. Self-x. Actually, that. And if you want to do an MLP from the you want to do an MLP from Swidelu, or from Xformers, you can do that by this. So I can do self.mlp is equal to Swidelu of the dimension, and you pass in, so you pass in the first dimension, and you pass in the hidden dimension. So this would be int of the dimension times the hidden scale. And then you pass in this other dimension. So it's basically the input dimension, the projection, and the output dimension that you pass in. And this does the exact same thing as the Swidelu MLP that was created before. It's just a lot more optimized. So now that we have that, let's go back to the paper. Basically, we have this input here, X or C, whichever one, since we're doing one stream. I'm going to look at C. So this is these are our embeddings. This is our class vector, and the class vector is, I guess it's for every layer, but yeah, basically it goes through this linear layer here. It then, so we have these norms here. These norms are already taken care of. Basically, that's what we did before. But it has these extra scales here. So we basically pass our embeddings through a norm. We pass it through attention. And the output of attention is, well, it has a residual, but it also has this scale parameter here, which is controlled by the class embedding itself. So you don't just have these residual connections here, you also have these class scales here. So the class information vector is also going to control the scale of the output, the variance of the output, in a way, by a linear projection. So that's what you see here, and that's why I have these extra projections here. Yeah, so let me just code that. Basically, the output of attention is going to be first. You want to normalize your inputs. So this is just normalizing our input like we did before, .norm1. So using the norm, the class is controlling the statistics of this. Then we pass that through attention, self.attention, and this will give us our output. And then you multiply by the scale 1 of y. This, like before, needs to be expanded because it is only a vector, so we expand it along this dimension to be a matrix. And then we add our output, or our input here. So this is the norm that you see right here, just the norm. This is the attention output of that norm. So we throw the normed input through, we throw it through attention, we get our output. The output is then scaled by our class information, which you see here. And finally, you have your residual connection right here. So that is that part. And the MLP is exactly the same, except I'm just going to return this. So it's exactly the same, except it uses norm2, so it uses a different norm. It uses the MLP instead of attention, and it uses a scale. So yeah, simple. This is our block. Nothing too complicated. And I'm not using Xformers because I was not using that right now. So let's make the diffusion model. This, I think we have, oh no, I need one more thing. I need to add a patchification block. So you need to patchify and unpatchify this image. It's very annoying to code. Basically, it uses similar functions as the convolution operation, which does this unrolling. So let me code that up. Patchify. Patchify.pop. Yeah, so let me do torch, import torch.neural-network.functional as f. All right, patchify. Yeah, there. Patchify. I can never spell that. Images and the patch size. So I'm doing a latent diffusion model, and the patch size they mentioned in the paper is a 2x2 patch, and I think the down projection is 8. So that is basically a 16 by 16 patch in pixel space, which corresponds to a 2 by 2 patch in the latent space. So that will end up being what you see whenever I code the diffusion model itself. Let me just patchify this. So nchw is equal to the images.shape, and then we have the patch height. I made it so you can change the patch sizes because I was curious to play around with that. So the annoying part with images and stuff is you have to calculate this padding. So I'll add this padding. It's nice that Copilot can just do that for me because of like writing this out. Yeah, so padding so that it goes to the shape of the patch size. So like if it was say 15 pixel or 15 by 15 image, then you have to pad it so that it can be divided by 2 by 2 on each side. So then we can just pad this by doing f.pad. It's nice that there's all this torch functionality already created. And then you do this patching by unfolding. The unfold operation was for the convolution, so you can do it efficiently, but it basically would take, like let's say we have a patch size of 4, it would take this and unroll it to 1, 1, 1, 1. I guess we can make that 2 and 3. So it would make that, I think it would be 1, 2, 1, 2. I don't remember which way it unfolds it exactly. It's one of the ways. So like the first part, so if we had a 2 by 2 window going across this, you would have 2 parts of your convolution. And you can turn this into a vector by unrolling it. And the unrolling operation or the unfolding operation basically unfolds every part of your image so that you can do this as a matrix multiplication with your convolution instead of a sliding window. The sliding windows are very slow on a GPU. So you would unroll this, and if this is our image here, just this 3 by 2 image, then you would unroll this, and we have a 2 by 2 window. You would unroll this into 2 parts, 2 vectors here, where our first vector is this first 2 by 2, and the second one is the second 2 by 2. So we're utilizing that exact same thing here, and yeah, Copilot already does it, so that you can just turn it into a vector easily. I forget exactly how it does how it represents all of this in memory, so I'm just going to write it out. I don't think the implementation here is that big of a deal, mainly because it gets convoluted with how all the dimensions and stuff work. So I'm just going to let Copilot finish this part for me. But the idea is the same. Contiguous dot view, that should be n. That should be -1. Patch height by patch width by c. nc -1 patch height patch width. Okay, so basically this unfolds it. I'm reshaping it to n by the number of patches that we have, by c, by the height, by the width. And then here I'm combining the last 3 dimensions. So I'm combining the channels, the height, and the width to the same dimension. And that's what you see here. Yeah. So that's patchify, and then unpatchify. Turn that. It just reverses that operation. And you need that so that you can reconstruct the image so that you can do the diffusion operation on it. I wonder how well it does this. That's not what I wanted at all. Unpatchify. I want to give it the patches. I want to give it the patch size, and I want to give it the original shape. I think it can infer that. It's just easier if I give it that the function that num patches and the patch dim is equal to the patch. Oh well, do it all. We'll see. So this is just taking this output as input here. So this is the batch size by the number of patches by the shape. That's what this is doing here. the height and width. So the number of patches I want to get for both the height and the width. So num patches h is equal to the original. So I'm passing in the original shape, so it makes it really easy. I can just get the original size, w original, get that from the original size. So getting the original size, this is just calculating the number of patches according to the height and the width. So number of patches on the height and the width. Then I'm just going to reshape them back to this dimension here, to this. So now that I know, like I know C, I know N, this gives me H and W. I know the number of patches, I know N, and I know the combination here. This gives me H and W, so I can then reshape this into C, H, and W. Reshape back to N num patches by C, H, and W. So that is C is equal to the patch dimension divided by the patch time. So that's just the remaining size, which should be 3, but I do not. It should be 3. Just do it dynamically just in case. Height, width, C, and yeah, that's good. And then I permute it and reshape. Oh yeah, this isn't combined. This is just number of patches on the height and the width uncombined, and then I would combine them together. This you need that if it's a rectangular image and not a square image. So permute back. 0, 3, 1, 4, 2, 5 dot view nc h patch height. Yeah, that's good. Yeah, GLO. There should be a function called GLO. Make a new activation function. And patches here. That's good. And this is just slicing off the padding. All right, that should work. Return images. There we go. I hate patchification stuff. It's just annoying to deal with, but you have to do it anyways. So that is that. Now let's actually make the diffusion model itself. I think everything is good. I think so. All right, so we have the models here, the blocks. Let me add models. I only have one model architecture, but this is how I laid it out in the code. This is diff model.py. Let's code this the rest of Stable Diffusion. Let's put everything together with this. So I'm just doing the stupid path hack again because I don't feel like worrying about relative paths. Helpers and blocks. I'm gonna need this later. Whenever I add the training code, I'm gonna need this part here. Import numpy as np. Import torch. You run into some issues with whenever you put it on multiple GPUs that are really annoying. So I added a few, like there are a few functions and helpers that I'm utilizing. It's not here yet, but I'll add it. All right, let's get positional encoding in here. Blocks dot positional. Oh, I did not code that part yet. Oh, right. So we also need a positional. So we have positional encoding 1 for the images, but we also need positional encoding 2 for the time step. So let me add that. I mean, this is just if we look at the transformer paper, I'm literally just going to implement that from Torch Import Neural Network. So if we just go to the attention is all you need, I'm just coding this part. Where is it? This part here. And that's because you just need a unique embedding for every time step that you have that's continuous, because I'm coding a flow model here. It's not a discrete diffusion model with 1,000 time steps. It's a flow-based model with that goes from 0 to 1, and this is just an easy way to code that since it's continuous. So class positional encoding of neural network.module, and all this is going to do self, dim, and device super dot other self dot dim. So all I have to do here is calculate the denominator here, this part. So we have the position here, so that's going to be our time step, and we can pre-calculate all of these here so that we don't have to calculate them every time. So self.denominator is equal to torch.tensor of 10,000. I know in Llama they use 500,000 here. I think it's 500,000 for the positional encodings for the sequence length. That's the rope theta that they use. But this is just the base frequency they use in this paper here. In the original attention is all you need, which is good enough, especially because it's just a time embedding. You just need a unique embedding for every time step. So yeah, let me do this. It's 2 times torch.arrange the dimension divided by the dimension dot to device. There. So all this is doing is it's doing 2 times the position in the dimension, 2 times I, divided by the dimension of the model here. So 2 times I divided by the model dimension, and you do 10,000 to the power of that. So that's the denominator. Yeah, so the forward pass, fine forward, self and time, will compute these embeddings, the sine and cosine part of the embeddings. So you have your embeddings here. So time is going to be of shape n. So it's going to be a batch of time steps that we have. And we want to encode this batch of time steps in using these frequencies that we created. And you can do that by just this code here. None. This is just adding a dimension there. Times self.denominator. I'll explain it in a sec. None. There. So this is just doing the product here. So this is our denominator. It should be negative, actually. Oh, wait, no, it's just divided. Yeah, it's fine. That's good. So embeddings of this. So every other embedding, if you look in the Transformers paper here, it is every other embedding is sine. So every even position is sine, and every odd position is cosine in the dimension. So that's what I'm going to do here. Basically, every even position, that's what we're getting here. Every even position, not on the embedding dimension, but on the dimension, or not on the batch dimension, on the embedding dimension, is going to be a sine. Is going to be computed or thrown through a sine function. That is there. And every odd is going to be thrown through cosine. So this is just getting every odd and it's throwing it through cosine. And then we return the embeddings themselves. So that's what is happening here. Yeah, that's good. So that's all. It's literally just computing this this here. That's all it's doing. I think that is good. I think so. Didn't miss any signs. Right. So now the diffusion model itself. Now that we have that, the positional gettings. Diffusion model. There we go. All right. So let's just start importing everything. src.blocks.transformer block. We're going to import the MLP. Actually, we don't need the MLP. We're going to import Patchify and blocks dot patchify. And we only need unpatchify. I'm using the Stable Diffusion 3 patchification strategy. I'll walk through that in a sec whenever I get to it, but we'll take a look at it in a sec. But it's basically patchification with a convolution. So it, instead of us just unrolling the patches, it does that with the convolution. So it can learn the filter instead of it being the identity filter. Import norm. And then from src.blocks.image positional encoding, which is I didn't code this before, this is from Stable Diffusion 3, the Hugging Face code. This is the patchification with positional, I removed the positional encoding, but patchification with the convolution. Import OS, import JSON. And from TQDM, import TQDM. There. Okay, now let's code this diffusion model. I call it diff model .module, and this is going to take in a bunch of stuff. So let's do self. It's going to take in the input channels. It's going to take in the number of classes. So this is 1,000 in the case of the dataset I'm working with. Patch size, the dimension of the model, the dimension of the class information, the hidden scale, which is 4.0, the number of heads, number of blocks that we're going to have, positional encoding strategy, the device, and some other information, start step, and wand BID. These two last things are for training. This would be for checkpointing, and this will also be for checkpointing. So yeah, let me just go ahead and write all these down. In channels equal to in channels, classes, patch size. Just let Copilot fill all the rest. There. All right, so then I have this parameter dictionary that I like to keep. Basically, these default parameters that will easily allow you to load the model. So self.defaults is equal to all of these parameters here. Well, all the parameters important to the model. So this will allow you to just pass this dictionary into the diffusion model and get that diffusion model out. Instead of having to manually adjust the parameters if you're playing around with the parameters themselves. Wand BID. I removed the starting step because I add that later. I am going to make this device always the GPU, so I don't have to worry about CPU versus GPU issues. So I'm just going to make self.device equal to CUDA. I'm not going to worry about changing that. All right, now let's get the blocks. So the blocks are going to be equal to the module list of just a stack of transformer blocks. There we go. So this is the model dimension, the class dimension, the hidden scale, the number of heads, the positional encoding, and the layer index. And we just do that for the number of blocks. So good old transformer. I love coding transformers after I have the blocks. It's just that. Then what we need is the time positional encodings. So let me go back to the paper. So we coded this. This is just one block here. And this over here is everything else. So I have this part here that I'm going to be working with. So like you're usually given a caption. You have all of these models here. Clip G14, clip L14, T5, extra large. And what you usually do is you would pass it through that model and you get out two embeddings. You would get out a pre-pooled embedding, so kind of this rich block of features where, like for clip, it's of size 77. I think clip L4, it's like 512. Clip G14, no, it's 768, and for clip L4, and for clip G14, I think it's 1268. That may be wrong. So you concatenate those together along the dimension axis, and you get this rich set of features from clip. And then you do the same for T5, except that is of shape 77 by 4096. And you can concatenate that together in this massive block. The rest is just zeros. And this would be your other stream. Like I said, I'm not doing the second stream because I can't do, like, I don't have that code ready yet. It's not, I'm not happy enough with it to kind of show it and talk through it. So I'm just doing single stream. So instead, you have this pooled output here. And instead of me doing the pooled output, I'm doing just a class embedding, which represents the same information. It's just not as fine-grained as a caption itself, because I'm not doing a caption model here, it's just a class-based model. But it's the same exact idea. You would take the pooled embeddings, and the pooled embeddings are one of the tokens here, and you take one of those tokens, the class token, and you throw it through this pooling layer, which is what the model actually uses, the clip model actually uses to do the similarity scores between the image and class, or between the image and text. So this is what you use on the left side here to control the outputs. So to control the statistics of whatever you're passing through the model. So that's what Y does here. So Y isn't just controlled by the class itself. Y is also controlled by the time step. So you have the time step here added, and the time step here is just the sinusoidal positional encodings that were coded earlier. So you have both the class information and the time step information controlling this modulation, which controls the statistics of every forward pass you do through the model. And that's what you see here. This big block here is just the second stream. I guess the big block is the first stream and the patches are the second stream, but we're just doing one stream. Additionally, yeah, this is the noise latent stream, and this is the text stream. So this is just the part we're coding, not this part here. I'm gonna have to figure, if I do a stream on that, I'm gonna have to figure out how to get that on my computer without it dying. I'm gonna have to use like floating point 8 or something to get that reduced. It's massive. Yeah, that is that. Let me go ahead and continue coding this part here. So the next part I'm adding is the time step. So self.t embedding is equal to the positional encoding, and that's wrong. The device is equal to self.device. Device dot to, we'll go ahead and ensure this thing's on the right device. T embedding 2. And this will be a linear layer. Equals neural network dot linear of the dimension and the dimension. I don't need self there. And no bias. There's one note I want to make in a second. We also need the class embedding. So C embedding, which is what is usually your pooled embedding, is nn.linear. .linear of self.num classes to cdim, bias equals false. So this is just a lookup table that I'm using. Like I said, usually this is a vector of information you use from the text, the pooled text vector. And then I'm putting this on the right device. There. And then finally, we have the C embedding part here. Dot linear. No. Cond embedding. No, so I'm gonna show you the code for training and I'm gonna talk through it. If I were to train it, it would take a really, really long time. And I'm also gonna give that code. The reason I'm not going through that is because, yeah, it takes forever. So unless you want to sit on a stream for a week, I'm showing the code. I'm going to talk through the training code. I'm not training the thing. I'm going to show you a trained version of the model, but I'm not showing you the training. So this is cdim by dim. So this is and then dot to device. There. So one thing to note is if we look at the paper here. So this is one part here. This is the other part. And y is basically sent through this linear layer after it's projected here. So, you project the class information, you project the time step, you add them together. That's what we'll have. And then we have this conditional embedding, which I just did once. If you have this conditional information, this conditional embedding layer be a MLP, for some reason the class information gets all messed up. I don't know what it was. I don't know why it does that. Maybe I wasn't training for long enough, but it kind of mixes up this class information. If I do, say, a nn dot, if I do a nn dot sequential. Oh yeah, yeah. The code is trainable. Yeah, so I'm gonna release the entire code base for this, and yeah, you should be able to use that for training your own model. I mean, I used it to train a model that is like it's decent. It's not awesome, mainly because I need to scale it larger. Like I don't I forget how much they used for Stable Diffusion 3. They used a ton of GPUs. I don't have that many GPUs, but yeah, you'll be able to use this for training. I use this for like research. I use this code to help me like with research stuff. So if I like have an idea for like if I have a research idea for diffusion, I can easily take this code, go and train it real quick on like you can do it on 1 or 2 GPUs, and you can get some results via the loss curve and the outputs. So hopefully it's helpful in that way, or at least hopefully it's a good base for that. But yeah, it is trainable, and it's trainable on multiple GPUs, and it should be trainable on multiple nodes. I have to double check that. I know that the Stable Diffusion 3 code that I have is, but I need to double check that this one is. So yeah. Um, yeah, I mean, so it basically it's just yeah, I can show that real quick. I'll show it at the. You want me to show that now? I could show it now, or I could show it at the end. Maybe once I'm done coding the diffusion model. But yeah, I can show you that. It literally just drops and it stays steady. It doesn't. It slightly decreases. It's exactly what you would expect. It's not. There's nothing special about it at all. Actually, I could probably go and get a snip real quick. Okay. Yeah, I'll show it later. Let me finish coding this part, but it's literally just the normal transformer loss curve that you see. Yeah. All right. So back to this part here that I was mentioning. If I have a sequential layer here, yeah, I'll show it then. If I have a sequential layer here, where I have the input as the number of classes. So this is going to take, the conditional embedding is going to take our text and class embedding, and it's going to project it to some dimensions that the model can use. This is dim. Neural network.silu, and I add another linear dimension. This messed it up a lot. Like if I had a MLP instead of a single affine transformation, you would give it like a class. I don't know if this is the same for text. I want to test that out, but you would give it a class, and I think it trained for 100,000. It trained for quite a while, and the output was just garbage. And I'm guessing that's because you get mixing of class information in some way. Like it kind of gets confused with this. Like it can't directly use the class information. Um, so that was something interesting I wanted to note in case you just it was something. It was a weird thing I found. So I'm like, oh, you just add an MLP and it'll make it better. It made it terrible. Didn't work at all. So let me add the patch embedding equals this linear layer projecting from the dimension to the dimension. Self dot positional positional encoding is equal to patch embed. So I'll go through patch embed in a sec. I think that would, yeah, the image positional encoding. Patch embed. Here. This is the stable diffusion. This was taken directly from Hugging Face off Stable Diffusion 3. Height equals 256. Width equals 256. The patch size equals the patch size, the number of input channels, layer norm. I think these are all the parameters they used that in the original Stable Diffusion 3 paper, or in their the Hugging Face implementation. Flatten equals true, bias equals false, interpolation scale equals 1. Positional embedding type. This is what I added. So this adds absolute positional embeddings. I changed that to rope because rope generally does a little bit better. And then send to device. So let me go through that real quick. The image positional encodings. So this is their thing here. Yeah, for Stable Diffusion 3. So it has this convolution here and this norm extra. And basically, in this forward method, it takes in a latent, and it does this projection here. And this projection is a convolution, like I mentioned before, the patchification strategy is a convolution. It uses the exact same code as a convolution, except the patchification strategy I coded does not have this patch information mixing. Basically, what this does is it will patchify it and throw it through an MLP, essentially. Or it does a convolution to do the patchification. So if we look at the projection here, it's literally the exact same thing, except they have a kernel going over it that is not the identity. Before, I coded an identity kernel, where it was just a kernel that does this patchification, and it doesn't do anything to it. This one, you use a kernel that does do it, and this is of shape patch size by patch size, and the stride is patch size. So it's a non-overlapping kernel that you have. And that's pretty much the only special thing they do. So then they flatten it, they add a layer norm just to normalize the inputs into the model, and that's about it. I don't crop or anything, so the rest is just normal. And then they add positional encodings. Like I said, I use rope, so I do not add this at all. I just make the zeros. Yeah, I make a none. So that is that part there. I'm basically just using a convolution instead of using a, like that's one thing they don't mention in the paper is this patchification strategy uses a convolution. Okay, now let's do the output norm. So if we look at the paper once more, we see this output has this normalization here. Modulation, I think, is the same thing as modulation here. So notice how it takes in the class and time information. So I think it's the exact same modulation. Then you have linear and unpatching. So this is going to be the output norm is equal to the norm C dim by dim, or dim by dim, and self.output projection is equal to the linear projection output. So this just projects it to the output. Patch size. This is the last output projection that was in the model. All right, so the VAE I use in here is Stable Diffusion, the original Stable Diffusion VAE. I didn't want to use the I don't want to use a Stable Diffusion. I don't know if they have. I don't know which one Stable Diffusion 3 uses. That was just because this one's really small, and the VAEs, it's good enough. So if you wanna use this code and make it better, maybe change out the VAE to something that is larger, something that is better, more modern. So I just used the original Stable Diffusion one though. Auto encoder KL. Self.vae is equal to this auto encoder KL dot from pre-trained, and this is stability AI ST FT EMA. So this is just the one I use. .eval. The downsample factor in here is 8. So we have a VAE downsample factor is equal to 8. So like I mentioned before, you have an 8, like you're doing a patch size of 2 by 2. And since you have an 8 times downsample factor, that basically gives you a patch size of 16 by 16 in pixel space and a patch size of 2 by 2 in the latent space. And we're going to freeze all the parameters in here. Self.vae equals self.vae. There we go. And I'm also going to cache this because I do not want this going in my root directory. It's always hidden, and I hate it going. I hate it going there. I mean, I know where it is. That folder just becomes massive. So, yeah, let me just start coding the forward pass. Forward. Self. So this will take in our input at time t. It'll take in a time step. It'll take in the class information, and it'll take in our null class information. So basically, this is just our input image. This is our time step. This is our class embedding vector, and this is node class, where node class basically is used for classifier free guidance. So if node class is 1, I'm going to make it where it masks the output to all zeros, and if node class is 0, then it won't mask it. So that's what this is here, just a mask. Exit time t, c, and null class. I actually don't need to make them. All right. Now for t, what we need to do is we need to project it. So t, I guess I should write out the shapes. Exit time t should be of shape b by c by l by w, or rather I'll make that n. So batch size, but just normal image shape, where it's channels first. T should be of shape n, so just the batch size. C should be of shape n as well, because we're not doing text class information. This is just a vector, and node class should also be of shape n, because that is just masking out the class information itself. So for the t information, we just send this through the t embedding, and then we send this through the t embedding projection here. Then, so that's literally all we do for the time step. It's getting the unique positional encoding and projecting that using a linear projection. Then what we do for the class information is we're going to first one-hot encode it. You can do this with an embedding table. It's just more verbose this way. So neural-network.functional.one-hot, where this input needs to be a long of type long, so int64. And the number of classes is equal to 1,000 in this case. And again, I want to reiterate, I'm doing this not because Stable Diffusion 3 does this, but because I just want to do a simple guided model with class information and not with text information. So normally you wouldn't do any of this. You would do just the C embedding part here, because C would already be a vector. Actually, you wouldn't even do this. You would just throw through a linear projection. Yeah. So before I send it through this, I also want to deal with the null classes. So the null class, where this is equal to 1, I'm going to multiply by 0. So basically, this is just getting a one-hot encoding representation of a class 1 out of 1,000. This is setting it equal to zeros if the class is null. So instead of there being a 1, it's all zeros, and then this is the embedding that we throw through, just to get a vector output. And then we throw this through the conditional MLP. So if you didn't have any of, is that up here? Oh, I called it condiment. Yeah, so if you didn't have this class information and you had text information, you would throw the text through here, where the text would be a vector, and you wouldn't have this. Well, you would have this part here, but you wouldn't have the rest. There. So that's the class information. Then our conditional information is t plus c. It's just adding them together. So that's this part here. Just get this part, add it together. This part comes from sinusoidal, this part comes from the text, which in our case is in text. Then what we need to do, yeah, and by the way, the original code is, or the code I'm going to send out is much more documented and much less of a mess than the code I'm writing right now. So yeah, don't think that this is the code I'm sending where it's like completely uncommented and stuff. There are a lot more comments. Exit time t. So we need the original shape because we're going to patchify this and then we're going to unpatchify it. So we're going to send this through the patchification. That is this patch embed here. I called it positional encoding because I initially used this as the absolute positional encoding embed, but it doesn't do the absolute positional encoding embed. It just does the rope later in the attention mechanism. So that is this part here. So this basically does the patchification, and it does not do the positional encoding because we're doing rope instead of absolute. But in normal stable diffusion, it would do the absolute positional embedding. Then we do the patch embedding. So that is this part here. T, so T in this case is the time step. If I go up here, yeah, T is the time step. C is going to be our class vector, or C is going to be our text vector that we're using. I think that's the same here. If you look at the paper, they use C for the class information, X for the input, and do they write out T anywhere? I don't think they write out T, but I use T as the time step. And that way it indexes X as well, so it's kind of consistent. For condiff, which part? Oh, yeah. All right, so this is just doing the patch embed here. So taking the noise latent, patchifying it, sending it through a linear layer, and I'm not adding positional embeddings because I'm doing that using rope. So then we're going to iterate over every single layer and just send it through block by block. Yes, a transformer. We love transformers because you can just do this. And they're good. But then once you send it through every single block with the input patches and the vector conditional information, where the vector conditional information is the time and the class information, you then need to send this through the output norm here. So the modulation via the class information and the output linear projection. This is self.out projection of self.output norm of the input, and this takes in y to modulate the input itself. And finally, we unpatchify this. Exit time t is equal to unpatchify exit time t, and this will take in self.patch size and the original shape. This is just the unpatchification strategy we had that I coded earlier. Exit time t. So what this does is it takes in, just to reiterate everything, this is basically the entire diffusion model. After this, I'm just going to add training code, inference code, and stuff like that. So yeah, this is the diffusion model itself. So it takes in our input exit time t. This is going to be our noise latent, where this is a pure image that we're dealing with. It would probably be better if you don't have to, well, since we use a convolution, you have to patchify it every time. But this is our noise latent. T is going to be our time step. That is some time step 0 to 1. C is going to be our class information. So in our case, it's a vector. But normally this would be or in our case, it's a single class value 0 to 999. So normally this would be a vector. And then null class, which tells us is this class information null or not, so we can do classify free guidance. T is then embedded using, if we go back to the paper, T is embedded using a sinusoidal positional embedding, so it gets a unique vector representation for our time step, and thrown through an MLP, where an MLP is just a linear layer in this case. C is our class information, and in our case, we are doing a embedding table. This is masking it, and I think I mask it, say, 10% of the time. I think they do. In the Stable Diffusion 3 paper, they mask it using a completely different mixture based off the T5 clip embeddings. So 10% is just arbitrary. Here, C is then sent through these embedding layers here, and then we add them together. So here, add it together, get our conditional vector. We then take xt, we patchify xt. No, this is Stable Diffusion 3. This is Stable Diffusion 3 with one channel, not the second channel. So there's two parts. You have the text and image streams. This is just one stream. So there's no text stream in our case, but it's the exact same architecture, except you don't have the second stream. So the input here is then patchified. It's then sent through this patchification embedding, and we send this through all the blocks, where the blocks, I'll go over those again. We send it through all the transformer blocks, and after we send it through the transformer blocks, where the class information is controlling the statistics of every part of those blocks, we have our output norm and our output projection here to basically send it the noise prediction. And then we unpatchify it to get it in the right shape. This doesn't have any parameters, by the way. Going through the transformer block, once more, we have our MLP, attention, and our two norms. So first, we normalize our inputs, control the statistics by the class information here. So that is this part right here, or rather right here. I keep on pointing to the left side, which is the class information, but it should be the right side. That is this part here, just normalizing it. The statistics control it, control the mean and variance of the input. We send this through attention, so throw it through attention. Like I mentioned, this is a single stream, so we do not have the text stream in this case because I'm not doing the dual stream operation, or I'm not doing dual stream, I'm just doing single stream. The output is then scaled by the class projection, or by the class vector, so that is this part here. And then we have our residual connection. One can think of this as a scale by the class information and a shift in a way as using the original input. So you can control both the, you both have this multiplication addition operation. I guess that's why they add that here. I'm not exactly sure how much of a difference this part makes, but they have it in there anyway. So yeah, that's that. You then normalize again here. For the MLP, you normalize the output of attention, and then you send it through the MLP here. You then have the scale here, so that scales the MLP output using the class information, and then you add the residual. So another thing to note in this diagram, if you look, yeah, thanks for being here. This was, yeah. Hope it was somewhat useful, but I'll send the code out later so you can play around with it yourself. Yeah, so this was, the one thing to note is x is the input here, and the residual x is added here and here, but that's wrong. That shouldn't happen. The input to the block should be added here, and the input into the MLP should be added right here. If you have the input into the entire block be added everywhere to the output of attention and the output of the MLP, it's much worse. So you want the input to be added to the output of attention and the output of attention to be added to the input. So like you see in a normal transformer, I think they just messed up the diagram here and it made it look a little bit, it made it look like I think they messed up the arrows here. So that's one thing to note. So that is that part. Yeah. Now let's start adding some other things on top of the diffusion model. So inference. I think inference is always cool. because then you can sample. Yeah, let me get the inference. Yeah. So to sample an image, you basically just have to do this iteration. So I'm going to do torch.nograd. Torch.nograd. This is assuming you have a pre-trained model and you can do inference with it. I do, and I'm going to send that out. Like I said, my model it's okay, but it works. It outputs okay things. I bet if you train it for longer and on more GPUs, it'll be better. But yeah, I don't have that hardware. Save. Just adding all these parameters here. Use TQDM. I'm gonna use TQDM. The sampler is boiler, and then there's a generator here. Generator to none. There we go. So this code is actually quite long, the sampling code. So first I'm going to, this is just used for training and stuff, which I don't have the training code yet. I'll show the training code after I show the inference code. But this is a loop on its own. You can just send it all this information and it'll be able to do the inference and send you the output image. So height and width are equal to 256. I didn't change that. So our output is going to be equal to torch.randn. So this is going to be our input noise. I'm just calling it output because it will be our output. So this will be of shape batch size by 4. So in the VAE, it outputs 4 channels instead of there being 3. So we're doing latent diffusion. So there's 4 channels. That's just the output. Height divided by 8. So remember that the scale, the VAE scale is this here. So it's 8 divided by the VAE scale. And the width is also divided by 8. So remember, since we're doing latent diffusion, we need to pass in noise of the same shape as the latent. So this is creating that noise here. And we use a generator. Generator equal generator. That's just for reproducibility. .2 self-talk device. Okay, so the null class, I'm just not going to worry about. That was in case you wanted to see what it would generate without a class. You can just look at that in the code. But yeah, I mean, it's basically just a mask. Torch.tensor class. Actually, I should probably add that. Label class label. So I'm going to generate a batch size of 2 here. So you can't do that with the code I'm writing here because the code is very specific for the diffusion model here. But you can do that with something like K-diffusion. You can directly pass it a pre-trained diffusion model, and it should work for that. I think would and you can use something like automatic 1111 for that. One of those interfaces. I think K-diffusion in general can. I think that's what they use in automatic 1111 actually. But no, this code is not general for all diffusion models. So this is just yeah, generating a batch size of 2. Actually, I'm just gonna batch size of 2. Actually, I have batch size here. So this is null guided. Yeah. Let me add null class. So like I said, we're doing CFG, and since we're doing CFG, you basically need to pass 2 images through. You need to pass the image through twice, and you can do that by just duplicating the batch twice. So you need to pass it once with the without guidance and once with the guidance, so then you can do CFG. And I'll show the formula later, but that's just what's happening here. So we have our batch size, I'm taking the class label, and I'm duplicating it twice, And for one of the class labels, I am making it 0. So like I have up here, we have this node class here. So I'm making the first one have node class, and I'm making the second one not have node class, so we can do CFG. So this will be 0 times batch size plus 1 times batch size. So all this is doing is creating a list that looks like this: 0, 1, 0, 1, and so on, depending on what batch size we have. And I'm going to make this a Boolean, and I'm going to send it to the device. And this here is just having one that's null and one that's not null. All right, images equal this. All right, so now what I'm going to do is I'm going to generate a set of time steps. Time steps is equal to torch.linspace from 1 to 0 plus 1.0 divided by number of steps. And we're going to have num steps, number of steps. So basically, this takes a range 1 to 0. So since we are training the model where 0 is going to be absolute image and 1 is going to be pure noise, we sample that image by generating in reverse. And we do that by starting at 1, and we iterate to 0. And what you do is you sample this depending on, or you basically interpolate this range for how many steps you want. So if we had 2 steps, it would just be this. Well, it would be 0, and it would be 1 and 0.5, because you don't have, I don't think you have the, like, you don't have the 0, because at time step 0, you have no noise. It's just image. And basically what this is saying is we have the model, if we have like the number of time steps, num steps equal to 2, then we have the model at time step 1, so pure noise, and we say, you give us the noise prediction at time 1. And what we're going to do is step with a step size of 0.5 using that output prediction. So then we're at time step 0.5, and we want to move to time step 0. So we then give the model the current noise image. We say you're at time step 0.5, so this is just telling the model what time step it's at, and then we step again with the step size of 0.5 to time step 0. So that's what this is doing here. We're starting at 1, and we don't end at 0. We end at 0 plus whatever this step size, or however many steps we're taking, because we don't have the model do inference at 0. We have the model step to 0. So that's what this is here. Then for t in TQDM of time steps, so we're just iterating over all the time steps, equals num steps, TQDM. And I'm going to make this false. So the CFG scale is just going to stay the same. You can make the CFG scale dynamic. I'm not going to worry about that right here. We're going to repeat the time steps for the batch size, or 2 times the batch size. So this is repeating the time steps for every part in the batch, but also since we're duplicating, since we double the image for CFG, we're doubling it here. So then we get to our velocity prediction from our model. So we finally do a forward pass, where the forward pass is what we wrote up here. So we get our output. I'm repeating the output twice. So our output is going to be of shape batch size by image size. And I'm repeating that twice because we need 2 forward passes. And then we just pass it all the other information we have up here. That should be output. And velocity is equal to, so now that we have this velocity prediction from the model, and this is training a flow-based model, I'll show you the code for that, but this model is a flow-based model. It is not a diffusion model. It's actually a flow-based model. I call it a diffusion model. It's a flow model. So the model is outputting a velocity. And if we have exit time 0 and exit time 1, then the velocity is going to point in the direction of exit time. Yeah, it'll point towards it'll point towards the change, so exit time 1. So velocity is pointing in this direction, from exit time 0 to exit time 1. And we can flip that so that we can move in the reverse direction. And you can train it either way. It doesn't matter. I just trained it in this way. I'll talk more about the velocity prediction whenever we get to the scale, or whenever we get to the training part. Dynamic times velocity from batch size minus the CFG scale times velocity batch size 2. Here. And I just made this normal. So this is the CFG, this is just normal CFG. It's 1 plus the CFG value, so we'll just call it alpha, times v without the class. So this is, v, no class, minus alpha times v with the class. So this is CFG like you've seen. Basically, if we let CFG be equal to 0, so if we let the CFG scale be equal to 0, let me just write that out here. You remove this, and you remove this here. So it's just the class prediction without any guidance. But if we let the CFG scale increase, so alpha increase, let's say we make it 2, then what we're saying is, like, we're keeping the original prediction, but wait, this is I have this reversed. This should be class and this should be no class. I'm like, wait, that doesn't sound right. Yeah. So if we have alpha be equal to 0, then you only have the class prediction. But if you have alpha be greater than 0, then basically you're removing the null information. So you have the model maker prediction with the class, and if you have CFG with an alpha or with the value greater than 1, then you're removing information that doesn't pertain the class at all. So you're moving more in the direction of the class. And that's what this is doing here. Right, yeah, because no class is 0 if we don't want to mask. Then dt is going to be equal to 1 over number of steps. So this is just our change in time. This right here is dx over dt, just velocity, and this is then what you do is an Euler step. So our output is equal to our output minus our velocity times dt. This is just normal Euler step. Our x at time t minus 1 is equal to x at time t minus v times dt, which is equal to x at time t minus dx times dt, so it's just moving in the direction of x. That's what you're doing. Normal Euler. Yeah, so that is that part there. I'm not I have some other samplers that I was playing around with, but I'm not going to worry about that. And eventually, this will give you an output. You iterate over this. I'm not going to worry about the other parts that I added in the code, but you then decode this using your VAE. So this is VAE decoding. And specifically, you need to scale it again, because the VAE has this scaling parameter. Config.scaling factor. And I'm going to clamp this. So I sample this, and I clamp it between -1 and 1. So what this does is it's taking the output. It is scaling it down. So with the VAE has some variance in the input. Like, you normally train the VAE so that it doesn't have this, so it doesn't deviate far from a normal distribution, but it will deviate from a normal distribution. And this is correcting for that variance. You correct whenever you're training before you send it through the VAE. This is just correcting after doing the inverse transformation. This is sampling from the VAE, and then we're just clamping between -1. And you do this part here because the image we're working with, I made it between -1 and 1. And then what you can do is you can add 1 to it, divide by 2, and then multiply by 255, and then you have your image in pixel space. This just makes sure it's in the range, because it'll be a little bit outside the range because it is a Gaussian that you're working with. And then just return output. Cool. That is that part there. Yeah, so this is sampling. Literally all it's doing is it's taking an input in the latent space. It's getting the labels. It's duplicating it twice so that you have um, a null forward pass and a class guided forward pass, and you just do inference by following the Euler sampling procedure by just sending it through the model, getting this velocity prediction, doing the classifier free guidance to that prediction, and just stepping along an Euler path. Note that this here takes the first half of the batch that has no. This is just taking the class guided, and this is getting the class unguided. That's what this is here. Yes, that is that part. Now I think I can talk about the training loop. Um, I'll send this code directly out, so if you want to play with inference, you can. I sent an example of one of the images whenever I posted that I was gonna do this, and you could see like the quality. What you could see it was, I think it was a cat. It was a cat, but there were some artifacts with it. So scale this up, see what happens. But yeah, let me do a training loop. So the training loop code is quite large. I think it may be better if I take the training code and instead of me, because there's a lot of parts to it that are just, I think I could just talk through it instead of writing it out, because writing it out I think would take way too long to do. So I think I'm going to do that. Um, yeah, because I enjoyed writing out the diffusion model. I think that was, I enjoyed writing it out. I think for the training code, it's just a lot of tricks and stuff. So let me go do that real quick. And that way you don't have to sit here forever waiting for me to get to this code. So let me turn off my screen real quick, and I will be back in or I'll put the code back on screen in a second. Uh, my bad. I fixed that. Yeah, I turned it down for a second. So you should be good. Thank you. Um, yeah. So what I was saying is the noise. We need to add noise batch. Sorry about that, y'all. Yeah. So we need to add noise batch, and what noise batch does is it's going to take our time step and it's going to interpolate it between it's going to take our image, it's going to take our time step, and it's going to interpolate the image between 0 and 1, time step 0 and time step 1. And at time step 0, we're going to have time step 0 we're going to have pure image, and at time step 1 we're going to have pure noise. So we're going to sample some noise. We're going to add that to the image with some interpolation. So here we have our x, which is just our image. We have t, which is going to be our set of time steps. We're going to randomly sample these in the training procedure. And here we randomly sample our noise from a Gaussian, so randn, that's our Gaussian sampling. And x at time t is going to be this interpolation here, where t is the interpolation parameter. So that's just coding this part here. And since you need the noise whenever you're training to know what to predict, I return the noise in the image. I do not think there's anything else. So let me talk through this step by step. I will use chain of thought on myself. So the trainer here, it's going to take in a bunch of stuff, but specifically it's going to take in a diffusion model, and it's going to take in a bunch of, a diffusion model, and it's going to take in some parameters like what batch size do you want to train with, the number of steps, the total number of steps you want to train for, the learning rate. I think I used 1e-4. Some EMA decay factors. So in the code, they use an exponentiated moving average. Moving average. Do they have that in here? Yes. Oh yeah, this is good. This is a good paragraph right here. So they have a learning rate of 10 to the -4, 1,000 linear warm-up steps. They use mixed precision training, which is what you would expect, and they keep a moving average of the model. So they have this model that is static, and they update the model as they're training so they update this static model every 100 steps. So you'll see that in the code. There's a static model kept on the CPU, and every 100 steps that the normal model is taking, it updates that model. So this will be a model with less noise because we're keeping a moving average of it. So it's less prone to noise within the data or within the training procedure. Decay vector of 0.99. Here, this is what I was mentioning before. They use this. This is the classifier free guidance percentage. They do this for the 3 text encoders independently. I just did 10% because I don't have any text encoders. So that's what you have. Learning rate scheduler, warm-up steps, exactly what they were saying. Unconditional, I made that 10%. And this here is for checkpointing, so that you can checkpoint the model. So this is just converting it from CPU to GPU. This here, so DDP, DDP is this, I think it's data distributed parallel, I think that's it. Basically what you do is it's the most naive way to do parallelism. If I basically am putting a copy of the model on, let's say I have 8 GPUs, this is going to put said model on 8 GPUs, and it's going to have them communicate. Let's say I have a batch size of like 16, and it's a small batch size, and I have 8 GPUs, then I will copy the model to all 8 GPUs, and if I want a global batch size of 16, then it'll take a batch size of 2, put it on each GPU, do a forward pass, and once they all do a forward pass of this batch size of 2, they will communicate after the forward pass and sync the gradients to get a global batch size of 16. So that's what DDP is doing here. The CPU just shouldn't work. Like it's here, but you should never train it on the CPU. I just had that for testing. And this is our EMA model here. So it's just copying the original model, and we're going to keep a copy on the CPU, and it'll be updated every 100 steps. AtomW, I have a different epsilon for floating point 16 here, but these are just the parameters that we usually use. Here, so you'll see this later, but if you're using mixed precision training, you need a grad scaler. Basically, it's to so you don't run into precision issues. You can scale it to larger numbers. Uh, so that's why there's a grad scaler here. But I'll show you later where you probably want to put it. Your optimizer, scheduler, and grad scaler just loaded in via checkpointing. More checkpointing, and here is a time sampler. So I'll talk about the time sampler in a second, but that's pretty important. There's some important stuff going on here. I'll talk about it in a second. So training here is just normal stuff, nothing special here. This is just creating the data set. I'm resizing 256 and I'm cropping it. So this is loading in the Imagenet dataset. And the reason I use this dataset was because Torch automatically they have this Imagenet dataset, so it makes it really easy to use. It's just there. Well, kind of. You still need to download it, but if you have it downloaded, then you can just use it by saying Torch Imagenet. So it should be easily reproducible here and relatively easy to use compared to other datasets. This is just cropping it, resizing, center crop. Center crop isn't good if you want to scale this up beyond 256, but it's good for pre-training. And then this is converting it between -1 and 1. So takes an image, interpolates it to 256, center crops it, and it moves it from 0 to 256 or 0 to 255 to -1 and 1. So make it a float because a model cannot work in the pixel space 0 to 255. And these are the data loaders. So this is just doing a random sampling data loader. This data loader isn't anything special. In the Stable Diffusion 3 code that I have, it is a lot more complicated, and that will take a while to go through. But here, it's literally just this here. Yes, this is weights and biases initialization. Nothing special here. It's just saying if a weights and biases ID exists, reuse that ID. So like if your job fails, you can just reload the model and start from where it left off. Otherwise, it makes a new one. And it's specifically watching the gradients as well. All right, finally, we're here. So to the actual training loop, enough setting up. So this iterates over it. It gets a batch of data in the step. The batch of data has the image, which I call batch x0, and the batch class. So this is just a class between 0 and 999, as well as the image of said class of size 256 by 256. This just ensures that it is of size 256 by 256. This shouldn't do anything, but it is there nonetheless. We then sample we then send this through the VAE. I'm doing that torch.nograd because we don't want the gradient of this. That would be useless. We're not training the VAE. Specifically, you send it through the VAE, you get the latent distribution, and you sample the latent distribution. So you don't just take the mean, which would be the latent distribution itself. You need to capture the entire distribution. So you sample it so that the model learns to capture the entire space of the VAE. It captures not the mean, but the entire distribution, the entire data distribution. So you want to sample it. Yeah, so make sure you're sampling. This here is the scale and shift factor that I mentioned before. So the variance of the VAE in the middle of the VAE, so after the encoder, is not it's not going to be a Gaussian. It's not going to be a normal distribution with mean 0 and standard deviation 1, although we would like it to be. This basically compensates for that in case the values are a lot larger. So this is just pre-computed. In the original Stable Diffusion paper, they talked about how you would get that, but it's basically sending a batch through, seeing what statistics there are, and fixing it because of those statistics. Time sampler. So I can start talking about that here. So if we look at the Stable Diffusion 3 paper again, a big point they made is the use of schedulers over here. So specifically, they said like this was the best scheduler, so I went with this. Tailored SNR samplers for rectified flow models. So basically you sample between 0 and 1, but they have this sampler here, which they found worked quite well. Well, I guess we can just read through it. Basically they say the RF loss trains the velocity v theta uniformly on all time steps. So if you think about it, if I am a model and I am trying to predict the velocity at any time step, it is quite easy for me to predict the velocity at the endpoints. If I am at x, if I get an image at x0, it says here, intuitively, however, the resulting velocity prediction target e minus x0 is more difficult for time steps in the middle, 0 to 1. Since for time step equal to 0, the optimal prediction is the mean of p1. So that would be the mean of the data, because that's an easy prediction to make. And for T1, the optimal prediction is the mean of P0, which is noise. So this is the noise distribution, and this is the data distribution. So the endpoints are really easy, while the midpoint is really hard because it's somewhere in the middle between one of these distributions. So it's a difficult prediction to make. In general, changing the distribution over T from the commonly used uniform distribution to a distribution with a density in the middle of the distribution, which is what this gives you here. It gives you higher density in the middle using a weighted loss. So basically it is weighing loss. It's weighing the loss where the time step is closer to 0.5 higher than at the endpoints. Does better. And they find that you actually need this to beat diffusion models in general. To beat, I think it was normal DDPM, or maybe it wasn't DDPM, but it was something like that. So rectified flow models need this extra loss term. So thus, we aim to give more weight to the intermediate steps. And you do that by just, like you have this here, this weighing term here. Like if we go to the loss function, up here, you have this loss, which is just the prediction, and you have this weight here. And the weight here is this. So this part here itself does the intermediate weighing, so weighs 0.5 higher than the endpoints. But this part here says how to do that. And they say here, one option for a distribution that puts more weight, so pi t, on intermediate steps is the logit normal distribution. So a Gaussian, as you would expect, if you throw a Gaussian at 0.5, it does that. It puts more weight on the in the middle than on the endpoints. So that's what they do here, and they say that in practice they sample the random variable u from a normal distribution here. So if we look again, basically this is our time step. This is our this is the time step we want to sample. I think that was here. But basically you change your sampling procedure. You can either change the loss function or you can change the sampling procedure. But if you change the loss function, you're still sampling uniformly, but the endpoints are getting sampled the same as the points in the middle of the distribution, but you're weighing the middle a lot. You're weighing the loss for the middle a lot more than the loss in the endpoints, and that can lead to problems of it not learning. Like technically to the limit, it's the same as what they mentioned down here, sampling differently, but it runs into problems stability-wise and training-wise in practice. So what you can do is you can change the way you sample time steps. So you keep the loss the same and you change the way you sample time steps to what they say here, where in practice we sample a random variable u from a normal distribution and map it through the standard logistic function. So this is what is done here. You are sampling u and you're mapping it through the logistic function here to get your sample time step. So here, this is taking just a Gaussian value, S and M. I think S and M are just one, so this is a unit Gaussian, mapping it through sigmoid, and that gives you what you want. And note that sigmoid is between 0 and 1, so this gives you a time step between 0 and 1 using u. So this puts more weight on the in the middle than on the endpoints. So this is what you can do instead. It's a lot easier to do this. So instead of sampling using a uniform distribution, you sample using this Gaussian, you throw it through a sigmoid, and you get weighted time steps. So the time steps are weighted themselves, not the loss. That is this. very important that this is done. If you look through the paper, if you don't have this, it doesn't work. P unconditional, this is a random value that I'm selecting. I'm saying if that random value is less than, so random value between 0 and 1, if that value is less than the probability, so 10%, then you get a value of 1. So you want to mask it, otherwise you don't mask it. So this is what we had in the diffusion model before. This here is noising the batch. So I mentioned before, this is what we added to the diffusion model here. It is taking the input and the time step, and it's just interpolating it via some noise, some Gaussian noise, and it is returning that. Here. So yeah, we get the noise that we want the model to predict, and we get the noisy input. This here is the autocasting functionality. This does autocasting where PyTorch sees like where it thinks it can do autocasting to half precision. So it doesn't cast everything, I don't think. Only places where it's mostly stable, and it can do this casting. So it saves a lot of memory to do if you do that. But yeah, this is just you can just add this and it does everything for you. So I don't have to worry about that. It's just adding that. I don't have to worry about casting everything myself. So send it through the model. This is the normal forward procedure we had, and the forward procedure doesn't care about the output. It just gives an output. We are going to interpret this output, however, as a velocity prediction, and we can interpret that via the loss function. So it gives us an output, and usually you can either predict the noise or you can predict we usually predict the noise, but instead we're predicting the velocity. So I have a really small derivation here, but basically the velocity is just the noise minus the image. So x at time 1 minus x at time 0. So this is the direction that we want the model to predict. This would be in the direction of the noise. And we're subtracting that, so we move backward in time whenever we're sampling. So we do the MSE loss between the output of the model, which we are interpreting as a velocity prediction, and the labels, which are the velocity, x1 minus x0. And yeah, that's our loss. This here is the weight. So you don't need this weight if you are doing the time step sampling differently, but you do need the weight if you are not doing the time step sampling differently. And this is just what you would use. This is a lot easier to mess up, and two, a lot more annoying to look at, and 3, not as stable. So just do the time step change. All right. So now that we have this loss, I made it where you can accumulate steps as well. Not a big deal, but here is the grad scaler. So you're using this floating point prediction loss, and this is scaling the gradients so that whenever it does a backward pass, it basically is more numerically stable. So you want that here. You want to scale the loss if you're doing automatic mixed precision and then do a backward pass. Just make sure you have this if you're doing AMP. Yeah, accumulation of losses and every number of steps. So if you make this 1, if you have accumulation steps equal to 1, then this doesn't matter. This is just 1. So every time we're updating the model, so self.gradscaler.unscale, this is unscaling the gradients. So here, this is scaling the gradients so that they're more numerically stable. This is unscaling them after the backward pass. So we scale them, we do a backward pass, and then we unscale them. More numerically stable, and then you do this so that you can actually update the model using the true gradients. Use AMP. So, for example, this may scale it by like 10,000 or something, and then this would unscale it by like 10,000. Here. So then you step using the grad scaler, and you step the optimizer. So normal optimization, and here, this is a scheduler step. So if you're using some type of scheduler, you would want to step it here. Grad scaler. I forget why the grad scaler needs to update, but it does need to update as you're optimizing the model, just like a time step, or just like the just like a normal learning rate scheduler. I forget why exactly, but you need that. And then here it's weights and biases logging. So every 100 steps, you update this exponentially moving average model. So every 100 steps, you are just updating the model. Yeah, of course. Hope you find it useful. I'm gonna send out the code later. But yeah, every 100 steps every 100 steps you are taking the current model, so the fast model, and you are updating it the old model, the slow model on the CPU, using a decay of 0.99. And that's what's being done here. So every parameter is decayed by that value. So this is saying we take that parameter, we are multiplying it by 0.99, and we are adding 0.1 times the new parameter. So this is just our moving average model that we're updating. And this is saving the model. So I have some things to save the model that are just, they're there. So hopefully the model you can easily load it in and stuff. Here, yeah, it saves the model and it takes parameters, it saves it to a file, and this loads the model. So it should be a lot easier to load later. So that is all the code pretty much. I think. Yeah. So hopefully that was useful. I can go ahead and do some sampling. The samples, like I said, they are okay. Like you get something like this or like this. They're okay. It needs to be trained for longer and higher scale. And two, I think the data is it's a really small data set for a diffusion model. So yeah, you could play around with it and stuff. But yeah, let me know if you have any questions. I think I think that's about it for the entire code base. Yeah, like I said, I'm going to send this out later. I'll send in an announcement out saying, oh, I got this code. I have the code. It's basically this code base here. I'm going to make it I'm going to clean it up a little bit, so hopefully it's easier to use. But I'm hoping this video was kind of helpful talking through it. Let me know, because this is the first time I've done something like this. Let me know if there's things I can fix, if there are some improvements I can make. I mean, there are. Let me know what those are. Yeah. But, I mean, if you want to play around with it, I can run this on I think 6 to 8 gigabytes of RAM pretty easily. So it's not that big, but it's fun to play around with and see what the model comes out with. Yeah, I'll end the stream in a few minutes. But yeah, thanks everybody for joining the stream. This was fun, cool. Yeah, but I will see y'all later. Have a good rest of y'all's day. I'm gonna end the stream here. Yeah, sorry. I'm still here, by the way. For if you got any questions, just fixing a few things up with the code behind a black screen. Yeah, before it ends. So yeah, sorry.